under the same starting conditions as before, but allowing the volume to go from 500 milliliters to 504 milliliters to allow for the displacement of some of the water into the tube, assuming the tube has a volume of 4 milliliters up to a height of 200 centimeters or 2 meters. We want to figure out what happens under those circumstances. Now, under those circumstances, there are three quantities that can vary: the temperature, the pressure, and the volume. So we're going to have to use PV equals nRT, and the one thing that remains constant is the what's remaining constant? Where are we? The volume changes, the pressure changes, the temperature changes. So all that remains constant is nR. The one thing that remains constant is the number of moles, because no gas is entering or escaping. Sorry, I had a little brain glitch there. Okay, so PV over T then will be constant, because PV over T is equal to nR, and N and R are both constant, meaning P1 V1 over T1 equals P2 V2 over T2. We could calculate then T2, solving for T2. It's going to be T1 times P2 V2 over P1 V1. And we could think of that as T2 times P2 over P1, the pressure ratio, times V2 over V1, the volume ratio. The pressure ratio is 6 to 5. The volume ratio, 504 over 500, is 1.008. If we multiply 6/10 by 1.008 and then multiply that by T1, we get something very close to 363 Kelvin. Put a question mark there, not sure about the decimals. That's a change of 63 Kelvin rather than 60 Kelvin. So just that minuscule change in the volume of the air requires probably more temperature change than you would anticipate. There are reasons for that, and maybe you would anticipate that. In any case, the next question is, what's the height of the water column to support the additional 20 kilopascals you get when you go from 100 to 200 to 120 kilopascals? Well, easy answer to that is that's the first thing we did practically in the whole semester, and we saw that a 2-meter height difference gives you 20 kilopascals. A column of water 2 meters deep gives you this pressure. But to work that out, I'd prefer to go to Bernoulli's equation, although there's an easier way to do it. Bernoulli's equation encompasses pretty much a bunch of other stuff. We note that the velocity of the fluid is not changing between the initial and the final state. There might be little velocity as the water rises, but it'll slow down and stop by the end, so that the initial velocity of the water was 0, the final velocity is 0. So the 1/2 rho v squared is not going to change. So the pressure change and the change in rho gy are equal and opposite, so that the change in rho gy is equal to the negative of the pressure change. Rho and g are constant, water being incompressible, so that the delta y is the only thing that changes over here, and we divide by the rho g, and we get this expression and this, and we get our 2 meters. And I'm not going to explain this except to say that the pressure difference from here to here is negative. We have more pressure here than we have here, so that the negative pressure difference from here to here gives us a positive change in our vertical position, which of course is what we do have.